No.
I see. Okay, it's 9 o'clock. Hello, good morning, good afternoon, and good evening. Welcome again to this World Large River and Delta System Source-to-sink webinar series. Today, we are very happy to invite Luca from University of Leeds at the UK give us talk about geological significance and source-to-sink controls on the classic parasequences. And before I introduce Luca, as always, I want to mention next Wednesday, we have Philip Menderhood. He's a graduate from Utrecht University, but now in Italy. So he will talk about the delta subsidence and sinking sinks is kind of, the delta subsiding, particularly in South Asia, Mekong River Delta. And he will give a little bit overview of the delta system also. And next Friday, and we have Bob Eller from Stony Brook. He will talk about tropical deltas, particularly focused on the carbon processing, mineralization, and the weathering process. As we all know, Bob visited China in 1979, the first member of the first delegation. So, so many of our colleagues know him. So please mark your calendar next Wednesday and next Friday. So, but one thing I want to point out to our European colleague, next Wednesday, because next week, this weekend, Europe will change back from summer saving time to a normal winter time. So only next week, US will wait 1 more week until November 1st. So there's a 1 hour difference from the previous talk. London will be 1 p.m. Paris will be 2 p.m. So US still 9 a.m., Beijing still 9 p.m. So this is the only change, only the 1 week difference. So the same thing as next Friday, London 1 p.m., Paris 2 p.m. So please take a note. And okay, Luca, graduate. Originally, he was from Italy. He got his bachelor and master degree from State University of Milan and master degree in 2010. And he went to UK, University of Leeds, and got his PhD degree 2015. And now, of course, he's working on the quantitatively the features of this delta progradation sedimentary architecture in the river deposition, riverine depositional clastic depositional system, and focused on the parasequences. So Luca, so now is your turn. Please share your screen and put a presentation mode.
Yes, should be able to. Yes, you should be able to see my screen, right?
Yes. Report presentation. Yeah.
Okay. Well, thanks, Paul, for the invitation to give this talk, and also thanks for organizing this seminar series, which has been great so far. And so, yes, as you said, I'm going to talk about clastic parasequences, and so stratigraphic units that record the regressive evolution of deltas and coasts. And I'm going to talk about the genetic significance of these units, and also how they're controlled by their sediment sources and by their sediment sinks. And the focus of the talk is really on the ancient stratigraphic record. So the record of ancient deltas and shoreline shelf systems. And so I guess you're probably aware of how a parasequence is defined. Parasequences were introduced in the 1980s as sequence stratigraphic units defined as conformable successions of genetically related strata bounded by flooding surfaces, where flooding surfaces are surfaces that mark an abrupt increase in water depth. And as defined originally, parasequences should be the record of paracycles, So while a sequence records a cycle of relative sea level change, a parasequence is a shallowing upward unit that records shoreline progradation, in theory, under positive accommodation. So, for example, episodes of shoreline advance and retreat because of variations in sediment supply or because of variations in subsidence rates. But in theory, there should never be a relative sea level fall during the evolution of a parasequence as originally defined. And parasequences are useful for stratigraphic correlations and reconstructions, and also for characterizing the architecture of hydrocarbon reservoirs and aquifers. There are actually some problems that make these units not ideal for sequence stratigraphic practice. Certainly the fact that it may be difficult to recognize a record of flooding beyond the shoreline, and also the fact that the drowning of parasequences may be just a local thing. But this, I think, that does not matter too much for the scopes of this talk, because the idea really is to just use data on parasequences to get some insight on how accommodation and sediment supply control stratigraphic architectures. And so parasequences are shallowing upward and typically also coarsening upward units generated by shoreline progradation. And they can be produced in different types of depositional environments, like river deltas or wave-dominated coasts with advancing strand plains. And so they can exist maybe as sets of deposits that include delta top, delta front, and prodelta, or coastal plain deposits passing to nearshore sands, foreshore and shoreface sands, down to the offshore transition zone and on the open shelf. But actually, the geological meaning of a parasequence can even be more varied than this. And in particular, a problem with the definition of parasequence is that it applies to units that can occur over different spatial and temporal scales, and potentially even to units that can be nested hierarchically. So if you think, for example, of the mechanisms of delta growth and abandonment, you have cycles of local progradation and drowning, but these can occur over a range of scales to form units like delta lobes or lobe complexes made of amalgamated lobes, and so on. And these units may all be treated as parasequences. So the definition of parasequence is easy to use, but it's a bit vague. So they can be a range of different things. And still, if we look at the geometry of parasequences and also their stacking patterns, so the stratigraphic arrangement of successive parasequences, they're thought to be controlled by two factors fundamentally: accommodation and sediment supply. And so if you consider how the parasequence is defined and generated, we can expect that their thickness will reflect the pre-existing accommodation, so the bathymetry of the shelf into which the coast progrades, but also the amount of accommodation that is generated at the shoreline, which itself is a function of the rate of creation of accommodation and the length of time over which aggradation takes place. So basically the lifetime of the parasequence. And then the thickness of a parasequence obviously can also reflect any possible erosion of their top, for example, because of wave ravinement, and also sediment compaction, which presumably will depend on lithology, diagenesis, boreal history, and so on. And if you consider the thickness of the nearshore sand belt contained in the parasequence, so the fascist belt that records sand deposition in the nearshore, the thickness of this sand body is also in part determined by the depth of the sand to mud transition on the shelf. And obviously, a deeper transition results in a thicker sand body. And this depth of sand mud transition will also control the lateral extent of these sand belts along the positional profile of the parasequences. And so a deeper sand mud transition will result in wider marine sand bodies that are more extensive along deep. But then the deep length of distant bodies will also be a function of shoreline progradation, which again is determined by the rate of progradation and by the duration of progradation. Now coming to the stacking patterns of the parasequences. These are commonly allogenic in origin, driven by variations in accommodation and in sediment supply. But because resolving the role of accommodation and sediment supply is not easy, we typically tend to reason in terms of variations in the ratio between accommodation and sediment supply. And so depending on the balance between accommodation and sediment supply, we see stacking patterns that are maybe progradational, aggradational, or retrogradational. And these are often characteristic of types of system structs. So for example, we expect to see progradational sets in ice-10 system structs, or downstepping patterns in falling stage system structs, in which parasequences can develop sometime during maybe still stands, so intervals of stasis in sea level. But then, even the stacking patterns, they may only reflect a local response, and they can be spatially variable. And so, for example, we can expect to see transitions from aggradational to progradational stacking in the same basin because of a reduction in subsidence rate along strike, or maybe a transition from progradational trends to retrogradational trends, depending on where we are relative to sediment input points that shifts in space, that translates in space. In this particular example, because of strike slip tectonics. So I was saying that it may be difficult to resolve accommodation from sediment supply, but there are actually some conceptual models that describe how parasequence thickness is expected to vary in response to variations in the rate of creation of accommodation. So accommodation alone, irrespective of sediment supply. So for example, if you believe that a sea level cycle can be described by a sinusoid, then you can assume that the thickness of parasequences may increase progressively through a transgressive system struct because of the progressive acceleration in relative sea level rise. And so you would expect a thickening trend. And in a similar way, I guess you would expect a thinning trend in an ice-10 system tract because of the progressive deceleration in relative sea level rise. And for the same reason, we can expect a shoreline trajectory that is concave towards the sea in ice-10 system tracts because of the relative increase in the rate of progradation relative to the rate of aggradation. If you're not familiar with the concept of shoreline trajectory, this is the trajectory that represents along a deep transect like this one, the position of the paleoshoreline through time in the stratigraphy. But the problem with these models is that they're just conceptual, and there are several reasons why they may not work. And for example, we may need to consider the effect of autogenic mechanisms, like the so-called delta auto retreat. So as a delta grows in size, the sediment volume sequestered on the delta top increases progressively, inducing a decrease in sediment flux to the shoreline. And so more sediment is needed to maintain the rate of progradation into deeper waters, especially as the subaqueous portion of the delta increases in size. And so we should expect an autogenic decrease in the rate of progradation, which should be reflected in a concave landward shoreline trajectory. And so you see how we may even see opposite trends in the same sort of context. And well, this was just by way of introduction. And coming to the work we did, what we wanted to do was to characterize the geological meaning of parasequences in the first place, and then also to determine the importance of geological controlling factors, and in particular accommodation and sediment supply on the anatomy and stratigraphic arrangement of parasequences. And we did this by looking at many different examples of parasequences, taking a database approach. And so we collected sedimentological data on many different successions, collecting data from the scientific literature and including those data in standardized format in a sedimentological database we have at Leeds, which is called the Shallow Marine Architecture Knowledge Store, SMAX. SMAX is a SQL relational database that we use for characterizing the sedimentary architecture and also the geomorphology of shallow marine and paralic depositional systems. And in SMAX, we digitize different types of sedimentary units that occur at multiple scales of observation. And we also include sequence stratigraphic units and surfaces. And so we also digitize parasequences and flooding surfaces. And all these units, they're described through a series of attributes, and they're assigned to case studies and the depositional systems and stratigraphic intervals, for which also we record a range of parameters describing geological boundary conditions and the depositional setting, but also metadata. And so effectively, the process of data collection consisted in digitizing sequence stratigraphic interpretations and all the associated data that are available in the published literature. And originally, this data were presented as interpreted correlation panels of outcrop exposures, or maybe correlation panels of borals in the subsurface, or maybe interpretations also of geophysical data sets. And so, yes, we took this sort of data, and here you see a summary of the data we collected. I've not included the full list of data sources. You can see we have over 130 literature sources, but you can look up the data sources in these two papers that we had recently in Sedimentology and Earth Science Reviews, which are free to access. Anyway, you can see that we collected data that come mostly from the ancient rock record, but also we have a few examples from the Quaternary. And okay, there is a bias towards the Upper Cretaceous, and actually also some geographic bias. And this is because of the many examples that we included that are from the Western Interior Seaway of North America. And this actually means that many of the examples we looked at are from a very specific kind of geological context. So from a shallow epicontinental sea in a back-tilted reservoir foreland basin, and from a time of greenhouse climate. Also here you get a sense of the data types that were used in the original studies from which we got the data. And the majority of the data that we used were from outcrop studies, but we have also used some subsurface examples. And here instead you get an idea of the size of the data that we considered. And the idea was to use this data to conduct a so-called meta-analysis. So a statistical analysis of the combination of many data sets, of many case studies. So as I said, in the database, we classify the depositional systems and the case studies, and we record different attributes to describe them. But we also store data on attributes that describe the sedimentary units. And for the parasequences in particular, we include data on their timescale and also on the interpreted origin. So for example, whether they were formed as deltaic units or as shoreface units, shoreface in a general sense, so as the product of migration of linear coasts, typically wave dominated. And we also characterize the geometry of these units. in terms of their thickness and the thickness and lateral extent of their shallow marine sand bodies, like delta front sands or nearshore sands. And with lateral extent, I mean as measured again along the positional dip. And also we record the amount of aggradation that takes place at the shoreline and the amount of shoreline progradation. And these two quantities will also be reflected in the so-called progradation angle, which again describes shoreline trajectory, but only like in the regressive evolution of the parasequence. And as I was saying, in the database, we include different types of sedimentary units, not just sequence stratigraphic units. And we also consider large-scale fascist belts that represent different environments of deposition. And we call these depositional tracts. And for this, again, we store different attributes, including their overall shoreline trajectory, which we can use in some cases to quantify the overall stacking pattern of the group of parasequences associated with that depositional tract. Okay, so we can start looking at the data. And really to start, I think it's useful to consider first how variable the data set is in terms of how the parasequences are characterized, and also to consider where there could be biases and sources of uncertainty that can affect our analysis. And so a first thing to consider is that typically we only have apparent measurements of morphometric parameters. So for example, of the thickness of parasequences, which will vary depending on where it is measured relative to the position of true maximum thickness. And so we may get differences in thickness statistics that just reflect variability in the degree of data coverage of the parasequence as a three-dimensional unit, but even just of its dip profile from onshore to offshore. I guess we can expect some differences in thickness, for example, to reflect the variable amount of aggradation that takes place along the positional dip. And what you see here is basically the relative frequency of parasequence thickness observations for the observation window, which is quite variable. So basically we go from cases where maybe you only see the parasequence in its nearshore part, which is case 4 here. And so the thickness we see there in this case is the thickness of the parasequence associated with that particular nearshore fascist sequence. But where we have maybe a wider observation window, like maybe covering the full the entire dip profile, which is the case 3 here, then we see that maybe the place where the parasequence is thickest may be somewhere else, and the value of thickness will necessarily tend to differ. And so basically you can see that the data set we have is quite heterogeneous in terms of how well the different parasequences are sampled. And this is because of data dimensionality and because of variability in data coverage. And obviously any comparison of the geometry of parasequences is affected by this variability. And so by uncertainty in local observations and in how representative they are. And then another problem to consider is that the data set includes a mix of outcrop and subsurface data. And also the subsurface data sets themselves, they're variable in terms of data types. So maybe they include some well data, but then maybe also some data from reflection seismics or ground penetrating radar and so on. And so the different examples can vary with regards to data dimensionality and resolution. And so if you look at data on the geometry of parasequences, like their thickness and the thickness and length of their sand belts, and we compare these across groups of data types, so examples from outcrop, from the subsurface, or from a combination of outcrop and subsurface observations, we see some important differences. Well, I should say, I'm not going to present the results of the statistical analysis because I would just make these slides too busy. But when I discussed differences across groups, these were all assessed by means of statistical tests, like in this case, analysis of variance. And you can find all the results of these statistical tests in the papers. I just didn't show them in the slides. And yeah, so looking at this data in particular, we see that parasequences recognized in the subsurface are on average thicker, but they tend to contain thinner shallow water sand belts, presumably because of apparent observations from well data. And these sand belts are on average much longer along their deep profile compared to the outcrop examples. And these are still outcrop examples for which the full deep extent of the units could be seen in outcrop. And so these differences in thickness and some body length are likely to reflect the effect of overcorrelation of units in subsurface datasets, presumably because of the amalgamation of regressive units that cannot be recognized in subsurface studies, especially where we have units that are laterally stacked as overlapping units with limited vertical offset. And so yes, we need to be careful where we handle different data types. But then the influence of interpretations on the results is not limited to how interpretations vary with data types. There is a more fundamental problem, which is the fact that the recognition of parasequences and the recognition of flooding surfaces are subjective exercises that are based on heuristics. And this means that any subdivision of the stratigraphy in parasequences is subjective and uncertain. And I think this becomes evident when we can look at classic, well-studied successions where we have different interpretations by different groups. And a good example of this is the Campanian and Black Oak Formation from the Shoreline Basin of the Western Interior in the US. And well, this is a succession that crops out in the Book Cliffs of Utah, where you have some fantastic outcrop exposures for tens of kilometers along the depositional dip. And for the Black Oak Formation, there are several studies documenting its organization in parasequences. And what we did here with these graphs was to compare three alternative sets of interpretations. So an earlier compilation by Tony Reynolds, a stratigraphic framework by Rianson and colleagues, and one by Simon Pattison. And you see that these interpretations differ in the number of parasequences that are recognized and also in the geometry of the shallow marine sandstones. And in some cases, these differences are important. And so basically, we need to consider this when we try to make comparisons between different case studies. So there is this subjectivity that makes it difficult to compare like with like. And so we need to consider this. And because of all these factors I've mentioned, so the fact that the definition of parasequence is very generic, and the fact that its application is somewhat subjective, and because of the variability in data types and data coverage across the case studies, because of all this, we can expect that the geological significance of parasequences is actually quite broad. And so that they include stratal packages that may vary significantly in terms of genetic mechanisms and also timescale of development. And this variability becomes evident where we can compare the timescale of deposition of parasequences in cases where we have some geochronometric constraints. And when parasequences were originally defined, it was assumed that they would reflect sediment accumulation at the timescale of tens to hundreds of thousands of years. And if you look at the examples for which we have some estimates of timescale of accumulation, we see that, well, maybe this is broadly true, but we see that parasequences actually cover 5 orders of magnitude in timescale of accumulation, from hundreds of years to over 1 million years. And in part, it is possible that this wide range of timescales reflects the difficulty in resolving true durations in the time, because of the difficulty in the difficulty to constrain the duration of gaps in sedimentation. And I will talk more about this in a minute. But then it is also likely that these results reflect, in part at least, the record of different formative mechanisms that are active over different time scales, but that generate similar products. So in particular, you see here some clear differences in the distributions of durations for quaternary parasequences in blue here, and for ancient parasequences. So pre-quaternary examples, but actually they're almost all Cretaceous. And this may reflect the fact that ancient parasequences are possibly more likely to represent a response to allogenic controls like orbital cycles. And actually, as you can see, we see two modes in the kind of ancient dataset that correspond broadly to Milankovitch periodicities. And while instead maybe quaternary parasequences, maybe they're more likely to record some higher frequency allogenic signal, like maybe still stands in sea level associated with stadials, or maybe impulses of sediment supply, and some more frequent variations in accommodation or sediment supply, which I guess we could expect for ice house conditions. It is actually also possible that these data on quaternary examples reflect the prevalence of deltaic parasequences in the quaternary dataset. And so that the shorter durations reflect the influence of photogenic dynamics. And I will talk more about that later. Another thing that we need to consider in this analysis is that because of the range of time scales covered by these parasequences, we can assume that estimations of durations and also estimations of rates of accretion, we can assume that these are affected by the so-called cellular effect. So we can expect that the average duration of breaks in sedimentation contained in the parasequences or associated with the flooding surfaces, we can expect that the average length of these time gaps increases with time scale. And this is important because it affects extrapolation of temporal durations, but also it affects estimation of aggradation and progradation rates in a way that these rates vary as a function of the time over which they're estimated. And in our data, we do see cellular effect because we see some negative relationships between the length of time of parasequence development and both their aggradation rate in the near shore and their shoreline progression rate. And these are broadly expressed as power laws. And I guess this is all expected because we know that shoreline progradation is not a steady process, but it's instead the result of episodic deposition, erosion, and reactivation at different time scales. Like we see in modern strand plains or also in deltas, where we see gaps in sedimentation that can develop because of photogenic mechanisms like delta lobe switching, and maybe also allogenic controls. For example, maybe changes in wind direction. And so this is something that we need to keep in mind if we want to make comparisons of progression rates, and also if we want to use these rates as proxies for sediment delivery rates. And we can also make some comparison of the geometries of parasequences developed at different time scales. And we see that parasequences of centennial to millennial time scale tend to be characterized by sunbelts and progression distances that are shorter than those of longer time scales. And these differences, again, they were tested and they are statistically significant. And they suggest that differences in time scales are not just apparent differences because of cellular effect and limited temporal resolution. Rather, these differences are telling us that there is variability in the length of time over which shoreline progradation took place. And probably also in the degree of lateral amalgamation of regressive units, and so also variability in our ability to identify flooding surfaces. And in general, because the units of smaller time scales are dominantly quaternary in age, we can infer that units classified as parasequences in the quaternary are maybe often not resolved as parasequences in the rock record. If they're recognized, maybe they're treated as bed sets or other informal units. So, as I was saying, in our database, we classify the parasequences in terms of the interpreted origin of their deposits, and also in terms of the process regime they record. Well, I should say actually that we rely on the original classifications as given by the original authors. And so we don't classify the parasequences if an interpretation is not given. We just rely on whatever interpretation is given in the original sources. And anyway, the idea is that we can look at this data on parasequence types to try to see whether there is a preferential depositional setting for the generation of stratal patterns that are classified as parasequences. And you can see that deltaic parasequences form around 1/3 of this data set, but also that the majority of parasequences that are classified are in fact interpreted with a product of wave-dominated environments, which also include wave-dominated deltas. Instead, tide-dominated examples, they represent less than 10% of the total, and you see that river-dominated examples are less than a quarter. We can also compare the geometry of parasequences and of parasequence bodies for units of different origin. And we see that deltaic parasequences tend to be, on average, thicker. And this is also true in cases where we only consider the true maximum thickness. And okay, we talked about types of bias and factors that can affect any analysis of this type. But I guess if we wanted to read something into this, we could try to interpret this in terms of a control of sediment delivery rates on progradation rates. And so on the shelf depth at which a delta is pushed during normal regression. And we do see that progradation rates are one order of magnitude larger in the deltaic examples compared to the progradation rates of short-phase parasequences. But the total progradation distance, so the total amount of shoreline progradation, this is larger on average for short-phase examples. And this is because they tend to record longer lengths of time. And we see similar differences when we compare wave and river-dominated examples, with river-dominated examples recording, on average, more rapid progradation, but smaller time scales, and so shorter shoreline progradation. And so this begs a question on whether there are fundamental differences across deltaic and short-phase parasequences in terms of formative mechanisms. I guess we could expect that in deltaic settings, where shoreline progradation is linked to river drainage, reorganization, and delta lobe growth and abandonment, maybe we could expect in these settings the generation of parasequences is a more punctuated process than it is for example, for strand plains, which are maybe more likely to experience steady progradation. So this is something to consider. At the same time, some differences between river and wave-dominated parasequences could reflect the control specifically of the wave regime on river avulsion frequencies. For example, because of the effect of longshore transport in preventing the lengthening and so also the gradation of distributaries, and so their tendency to avulse, or maybe because of the confinement imposed by sets of beach ridges that are elevated and that can develop in this sort of wave-dominated context. And so basically we could wonder whether data on the time scale and on the anatomy of short-phase and deltaic parasequences, whether this data reflect somehow some differences in the record of allogenic controls and autogenic processes across deltaic and short-phase systems. And so to see if these differences in parasequence characteristics could be due to the influence of coastal morphodynamics on the tempo of parasequence generation and the mechanisms of parasequence generation. We try to look at some additional data, considering data from the shallow subsurface of some modern deltas. And in particular, we looked at Mississippi, the Burdekin, the Ebro, the Po, the Rhone, and the Yellow River. And we really just wanted to compare observations on parasequences with data on deltaic constructional units, and in particular on data on delta lobes. And this is because it is often assumed that a deltaic parasequence represents the preserved record of delta lobe. So the process of delta lobe switching in response to river avulsion is commonly considered as an autogenic mechanism for the generation of parasequences. But I think that I guess we need to consider before we make any comparison is the fact that as a geological entity, a delta lobe is only vaguely defined. And the data sets we considered, they all share the view that a delta lobe is a sedimentary body that represents a stage of delta construction in relation to a state of river drainage. And also they all share the view that a lobe is made of genetically related delta front, delta top, delta front, and pro-delta deposits. But the problem is that still this definition can be applied to units at different scales, depending on the scale at which we consider changes in sediment dispersal. And I think in the end, this is reflected in the fact that, as I was saying at the beginning, there are different hierarchies of deltaic units that are established sometime. And so, like we have delta lobes, we may have higher order units made of coalescing lobes, like maybe lobe complexes, super lobes, or whatever name they're given. And so, again, making sure that we compare like with like is not straightforward. So even though this definition of delta lobe is vague, we still consider cases in which the term delta lobe was used in this way. But we also consider data on deltaic constructional units of a higher hierarchical level, and so of a larger scale, so lobe complexes and so on. And so we can compare the spatial and the temporal scale of these deltaic units with the scale of deltaic parasequences. And we see that the time scale of construction of both delta lobes and of the higher scale constructional units that they form, this is on average shorter than the duration of deltaic parasequences. And the difference is by one order of magnitude when we compare delta lobes and parasequences. We also see that ancient deltaic parasequences are on average thicker than delta lobes, even though they record greater sediment compaction, because they're mostly all ancient examples. And obviously, when we compare data on durations, we know that the comparison is affected by the difficulty in constraining the duration of time gaps. But still, the combined data on the spatial and temporal significance of the units, I think it suggests that maybe the majority of deltaic parasequences that we define in the rock record are actually likely to contain several amalgamated delta lobes, rather than just representing the preserved expression of a delta lobe. And so, yes, if deltaic parasequences are dominantly autogenic in origin, maybe they are more likely to reflect major reconfigurations of fluvial drainage, rather than delta lobe switching in response to localized avulsion on the delta plains. So moving on to the analysis of the record of accommodation and sediment supply. But I guess I should spend some words on the limitations that affect this type of study. But actually, I think I've covered most of this in the previous slides. Maybe a thing to consider that I did not mention is the fact that when we look at shallow marine sandbelts, we refer to the boundary as traced by the original authors, the author from which we got the data. But in reality, that boundary may just be a gradual transition. And then also there is the issue of comparing shoreline trajectories and progradation angles, because these are affected by error in measurements, and especially considering that we're typically dealing with very small angles. And also when we need to handle shoreline trajectories, another problem is the choice of a datum that can be considered as fairly horizontal. So that's another problem to consider. And then also the angles that are affected by sediment compaction and variable sediment compaction, and we did not decompact those angles. Yeah, but still we try to do this work, and we looked at how properties of parasequences vary in relation to attributes that describe the balance between accommodation and sediment supply at different scales. And at the scale of the parasequence set, so in a stack of parasequences, we can look at differences across stacking patterns, from progradational to aggradational to retrogradational. And we see that the majority of parasequences are recognized in progradational sets. And we see that in these sets, parasequences tend to be thicker on average, which is maybe not what we would expect, given how parasequence thickness is supposed to be controlled in part by the rate of creation of accommodation. And so parasequences from retrogradational sets, they're relatively thinner on average. But this can be explained in part by the fact that these parasequences are likely to be truncated at the top by ravinement surfaces produced by wave erosion as the shoreline retreats. And this is consistent with this observation that the thickness of parasequences topped by ravinements tends to be smaller. And then we also looked at variations in the thickness and in the deep length of shallow marine sandbelts of the parasequences across types of parasequence sets. And we see that progradational sets also contain parasequences with sandbelts that are on average thicker and more laterally extensive along dip than those in aggradational or retrogradational sets. And I should point out that this scale is logarithmic, so the difference is actually quite important. And for parasequence sets, we also see that the stratigraphic rise of parasequences, so the amount of aggradation recorded at the shoreline, is larger on average in progradational sets, which is probably unexpected. But then, as we could expect, the progradation distance, so the amount of shoreline progradation, is also larger on average for parasequences in progradational sets, and smaller on average for retrogradational sets. And so in the end, the progradation angle of parasequences is on average smallest in progradational sets and on average larger in retrogradational sets. So relative to the gradation rates, parasequences in progradational sets will tend to record a faster progradation, as we could expect perhaps. And so these differences in stratigraphic rise, which look a bit odd, I think they probably just reflect differences in parasequence duration, because the development of parasequences is more punctuated under transgressive conditions. And we can do a similar analysis for system structs, which also describe a relationship between accommodation and sediment supply, but with respect to the phase of a relative sea level cycle. And in this case, we see that the majority of the parasequences were recognized in high-stand system structs. And we see that the parasequences tend to be thicker on average in high-stand and low-stand system structs, and thinner on average in falling stage and transgressive system structs. And this again may be because of erosive processes during regression and transgression. But then it means that higher rates of creation of accommodation don't correspond typically to thicker parasequences, as it is often implied. And also another thing to consider is that the fact that progradational sets and I-stand system structs tend to contain thicker parasequences, I think it may reflect the fact that the parasequence thickness may be related to the amount of progradation recorded in the parasequence, in the sense that progradation in deeper shelf areas may result in the end in thicker parasequences. And if we look at data on parasequence and belts, we see that they are on average thinner and narrower in transgressive and falling stage system structs. And this difference in sunbelt thickness can be again interpreted in terms of controls played by erosional ravinement in transgressive system structs and by negative accommodation in falling stage system structs. And instead differences in the sun-body length, I guess that can be interpreted in terms of parasequence generation being more punctuated under conditions of relative sea level rise or fall. And then presumably also processes of cannibalization are more frequent in these conditions. And actually, several of the examples that we included as force regressive parasequences, I think I should point out that they are not actually true parasequences in the strict sense, because they record the positions under conditions of relative sea level fall, and not just during still stands in the overall falling stage. And so they are actually not orthodox parasequences. And we see this where we can look at these falling stage examples that have negative stratigraphic rise. If you look at the progression distance of the parasequences, we see that it tends to be lowest in transgressive system structs and highest on average in falling stage system structs. I guess this is all expected given the overall trends of shoreline shift in these two types of system structs. So in this case, we have progradation in line with the allogenic trend, and in this case, against the direction of relative sea level change. And so these observations, together with the corresponding results for the parasequence sets that I showed earlier, they suggest that rapid shifts in shoreline position are likely to determine punctuation in parasequence organization that in the end affects the anatomy of the parasequences. So at the beginning, I was talking about the fact that in some system structs, we can expect to see some trends in parasequence thickness, which would reflect variations in the rate of creation of accommodation. And to see whether these trends are recorded in the studied examples, we looked at distributions of the change in thickness across pairs of successive parasequences. And what we see is that, while the data are really not much in agreement with the models, we see a dominantly thinning trend in I-stand system structs, and also a bit of thickening trend in transgressive system structs, but these trends are actually very subtle. And yes, we may also expect some trends in parasequence progradation angle and progression distance in series of stacked parasequences, which could reflect, for example, concave seaward shoreline trajectories in I-stand system structs. And so to quantify these tendencies, we can look at variations in parasequence progression angle and parasequence progression distance across pairs. But if we look at these variations in I-stand and low-stand system structs, we see that actually there is no preferential trend of shoreline trajectory. And this could be, well, for many reasons. For example, because of variability in the duration of parasequences, or because of the interference of autogenic dynamics. And we are talking, for example, about the delta auto-retreat, which would cause concave landward shoreline trajectories, or maybe also because of the fact that accommodation generation does not just follow a simple sinusoidal curve, or maybe also because sediment supply rates are more important. And going back to controls on parasequence thickness and on the possible role of sediment supply, in general, we assume that the thickness of a parasequence is determined in part by the amount of aggradation it records, and in part by the pre-existing accommodation. So by the depth of the shelf into which the shoreline progrades. And we see that both factors seem to be important because we see some positive relationship between thickness and stratigraphic rise, and also between thickness and progradation distance. And of course, the relationship between thickness and progradation distance may be spurious. It could just reflect the fact that the longer the time embodied in a parasequence, the longer the progradation distance on average, and so the greater also the stratigraphic rise. And we see this in our data because we see a positive relationship between stratigraphic rise and progradation distance. And so it is maybe more useful to look at rates, and we can look at relationships between aggradation or progradation rates and parasequence thickness. The problem again is that these rates really depend on the time scale at which they're evaluated because of the cellular effect I mentioned before. But if we break down this analysis by time scale, we see that the thickness of parasequences tends to correlate directly with both aggradation and progradation rates. And okay, these correlations are not very strong, but I guess this is expected, especially if you consider the effect of shelf bathymetry on the rates of shelf transit, where if you have maybe a steeper continental shelf with a deeper margin, we may expect to generate thicker parasequences, but this will presumably be associated with slower rates of progradation. And we also looked at the relationship between mean progradation rate and the horizontal extent of the parasequence and belts. And again, we don't really see any correlation between progradation rate and some body length for the entire pool of data, but we see positive relationships between these variables for the different time scales. And in general, the progradation rates can be controlled by the bathymetry of the shelf, in the sense that the accommodation is filled more rapidly in a shallower shelf, in the sense that the accommodation is filled in a way that progradation can be faster. But because of the results I showed earlier in the previous slide, where I was showing a positive correlation between parasequence thickness and progradation rate and distance, because of this, I think it is sensible to consider the progradation rate in these examples as a potential proxy for the rate of sediment supply at the parasequence scale. And then if we look at how the parasequence progradation angle is defined, this is a measure of the ratio between the stratigraphic rise and the progradation distance. And so we can use this progradation angle as a proxy for the ratio between the rate of creation of accommodation at the shoreline and the rate of sediment supply at the parasequence scale. And what we see is that for units with negative angles, so parasequences in inverted commas associated with forced regression, we see that for these units, well, they tend to be thicker and to contain thicker and longer sunbelts on average for flatter progradation angles. And the same is true for parasequences with positive progradation angles, because they're on average thicker and with thicker and longer sunbelts for flatter progradation angles closer to zero. And I guess this is all in agreement with the results we've shown so far. So faster progradation into deeper shelf areas driven by faster sediment delivery rates will result in thicker parasequences with more extensive nearshore sun bodies. Obviously, I guess we need to be careful with this because well, this data should really reflect measurements that are taken along deep-oriented profiles, because if we include apparent measurements, the progradation angle will decrease because it becomes an apparent angle, and the length will increase because we measure it at an angle that gets closer to the orientation of the paleo shoreline. And because we also record the shoreline trajectories of so-called depositional tracts, so fascist belts that span several parasequences, we can also quantify relationships between larger scale progradational trends and the extent of some bodies reflecting parasequence scale shoreline advances. And again, also this scale, we see some moderate negative relationship between the shoreline trajectories at the larger scale and the average sun length of the parasequences, which I guess, again, can be interpreted in terms of a potential control of sediment supply rates, but in this case over different time scales. Okay, so we talked about differences in parasequence characteristics across types of parasequence sets and system structs, which can be interpreted in terms of variations in accommodation and sediment supply. We also talked about differences in how parasequence characteristics may be displayed in the relation to their origin. And I think it's useful to look at how these properties may be related. And I'm sure you are familiar with this classic model of how the configuration of clastic coasts is expected to vary as a function of relative sea level change and sediment supply rates, with transgressive coasts being dominated by barrier island systems and estuaries, and regressive coasts dominated by deltas and strand plains. And we can look at the relative frequencies of parasequences interpreted as the product of deltas and linear coasts across types of parasequence sets and system structs. And the differences are not as important as we may have imagined, but we see, for example, that deltaic parasequences are relatively more frequent in progradational sets, and also that fluvial-dominated parasequences are mostly associated with progradational conditions and ice-stand system structs. And so one thing to consider is whether variations in sediment supply along shore can determine differences in the positional system type, but at the same time, maybe also to cause some lateral variability in parasequence architecture, like in stacking patterns. So it is possible that in part, these results reflect the role of sediment supply on the development of river deltas, but also as a driver of the positional regression. Okay, because we know that sediment supply rates control the deep extent of parasequence and bodies, we may want to be able to use some metrics that describe controls on sediment budgets for deltas to make predictions of stratigraphic architectures. For example, for predicting the architecture of deltaic hydrocarbon reservoirs or coastal aquifers. And so we can look at estimates of the size of drainage areas fed the paleodeltas, which can be based on paleogeographic reconstructions or paleohydrologic reconstructions. And we can also look at estimates of maximum bankful depths of the channels of coastal rivers. And this can be based on sedimentological data. And we did this, and in particular, we looked at data showing how these quantities relate to the mean length of parasequence and bodies in Cretaceous successions, again, of the Western Interior Seaway in North America. We also plotted the data on the Po and on the Rhone, so on quaternary examples, but just as a reference. The advantage of having focused on the Western Interior is that all the examples are from a specific geological context, but then the disadvantage really for this type of analysis is that we did not consider examples of large river systems. So ideally, we really need to expand this sort of analysis. But overall, we see the positive relationships that I guess we might have expected. But yes, with a lot of scatter, a lot of variability, which is not surprising, I imagine, because we have a lot of uncertainty in the data, and not just because of parasequence attribution, but also because of potential error in the measurements and uncertainty in our ability to constrain these variables. And then another thing to consider is that well, increased rates of water and sediment delivery. They favor the formation of deltas over wave-dominated linear coasts. This is something that Rebecca Caldwell was talking about last week. And so obviously, based on what we showed today, deltaic parasequences may be more punctuated because of autogenic dynamics. And so in the end, this may also be reflected in this data. So, well, yes, I think I've gone on for way too long, probably. So rather than repeating myself, I suggest that maybe you just look at these two papers that we have in our science reviews and in sedimentology if you're interested in the details of the work. And yes, now maybe it's time to take some questions. And I just want to say thanks to the sponsors of our research group for funding this work. And well, thank you for your attention.
Okay, thank you, Luca, for this very comprehensive, fantastic talk about sequence stratigraphy. So if you have any question, you can go ahead to raise your hand, or you can unmute yourself. Now I just turn the function on. So you can just go ahead and ask a question. So before anybody jump into a question, Luca, I have a question. Here you tackle fantastic about the relationship of sediment import and the sea level history, and even the is a transpiration, was a regression, progradation, retrogradation. So that's great. You also use a lot of ancient delta, old sequence stratigraphy data. We all know the past is the key for the future, but at the same time, the present is also a key for the past. And what the reason I see this, because if you look at many modern, the present, the modern river sediment and the delta progradation, it's not only that, sea level and sediment discharge. It's not only that cross shelf, understand very well the claniform. There's a major portion of the riverine sediment was carried away from the proximal depot center and distributed all the way along the shore. So if you look at ancient sediment record, that might be not necessarily directly linked to a river mouth. The sediment discharge is not really a archive of the cross-shelf, sediment transport. So do you see what I mean?
Yeah, obviously there is this component of the sediment budget that is exported beyond. And obviously this is something that I guess it is probably difficult to take into account in sequence stratigraphy. So what question do you want to make specifically about this?
I mean, what I mean is some old record, it looks like a beautiful claniform cross shelf, could sometimes be misinterpreted. For example, we see the longshore drifting claniform still form that kind of, cross shore claniform looks like a regressional deposits, or sometimes looks like the FSST, the falling stage system tract. But actually it's not, because this is the longshore drifting. If you look at your home country, the Po River in the Adriatic Sea, and also your friend Stefano Paterno, his recent review of that longshore drifting and sediment stratigraphy. I mean, sometimes based on the old record, could be a little bit misinterpreted.
Well, yes, I guess as I was trying to explain, a lot of what we put into sequence stratigraphic interpretation have significant variability in terms of genetic significance. Mm-hmm. And yes, potentially a way forward is a better integration between sequence stratigraphy and fascist models with improved consideration of the genetic mechanisms of stratigraphic products.
Yeah, I think maybe next step, we need to put the proximal and the distal, the longshore, cross-shore, and the longshore together to get the whole 3D view of the sequence stratigraphy. Okay, anybody else, any question? If you have any question, you can go ahead to unmute yourself or, Adlik.
Yeah, I have a question.
Yeah, go ahead.
Yeah, very interesting talk. Do you have any example from Sunda Shelf?
On the Sunda Shelf?
Yes.
The Gulf of Thailand, well, it's not part of this database.
Oh, okay. Okay, thank you.
You can find the entire list of sources in the two papers. It was like 130 publications, so I just didn't include it here. But yeah, if you're interested to know in the examples, you can just look it up.
Okay, thank you.
Thanks.
Okay, anybody else? Okay, and so anyway, I know there's a lot of information in Luca's talk. If you want to look at more closely, a little bit closer, so you can rewatch this presentation on the YouTube, and it will be, it's on there now, but the edited version will be ready in 24 hours. And so once again, this next week, next Wednesday, Philip Mandelhood, he will talk about the delta subsidence. And also next Friday, our old friend Bob Allen, next Friday, he will talk about the carbon process and mineralization. So please remember, as I mentioned at the time, so we'll be a little bit different in Europe because from this weekend, Europe will change back from the summer season time to the normal winter time. So it's 1 p.m. in London and 2 p.m. in Paris, and only next week. After November, US and Europe will be same back to normal. So I think thank you very much. If no any other question, Luca, thank you very much for your wonderful talk, and it is a great work. If possible, I would also suggest to look at the Sunda Shelf and also the Vietnam Shelf, a lot of seismic, a lot of that kind of data, and offshore of the Yangtze, and the recent work of Irrawaddy and the Ganges Brahmaputra. Okay.
Thanks for the suggestion. I can make available the PowerPoint.
Oh, that will be very, very, very appreciated. I will, we will share to this community, and many young, many students and graduate students will benefit. Thank you very much. So I hope you have everybody have a good day. That's great.